All right. So it's with a great pleasure having Dr. Shira Raveh-Rubin here as today's Towers seminar speaker. She is zooming in from the Weizmann Institute in Israel, coming from the Department of Earth and Planetary Sciences. And I really appreciate taking time for the seminar. It's evening now, dinner time, I assume, in Israel. And a few words to Shira and how we met. Shira and I met regarding was a DOE-funded field campaign, and as you know, I'm an aerosol scientist, and that was a field campaign around the Azores, trying to understand microphysical properties of clouds. And Shira pointed out that in wintertime, there are the effects of dry intrusions, which move air from the upper troposphere to the marine boundary layer, and that could affect aerosol population, aerosol chemistry, and cloud formation. And so we got in touch via this, coupling of dynamics and aerosol population. And I'm not saying more because Shira will tell us all about dry intrusions. A few words to her career. She did her bachelor degree and master's degree at the Hebrew University of Jerusalem, both with cum laude, and got awards for this work. Her PhD then was done at the Weizmann Institute in the Department of Environmental Science and Energy Research, and her thesis title was Anomalous Non-Conservative Chemical Transport in Saturated Porous Media. So
very different.
Branched out from atmospheric sciences. But then here comes a common past of both. She did a postdoctoral fellowship at the Swiss Federal Institute of Technology in Zurich, and her advisor host was Professor Heini Wernli. And I was there as a grad student. I was in Heini's and Hugh Davis's classes in dynamics. I had to take extra classes because I was not yet a full atmospheric scientist. And so there was some overlap. Currently, she is a senior scientist at the Weizmann Institute in the Department of Earth and Planetary Sciences. I want to point out or highlight, she got this year a very prestigious award, the Scientific Council Prize of the Weizmann Institute of Sciences. There are several other ones. I'm not going through all that. She is very active in many committees. I want to highlight that she is an editor of a rather new journal at the European Geosciences Union. That is the Journal of Weather and Climate Dynamics. So in case you have a topic that's in this open access journal, get in touch with Shira. And that is it for me. Without further ado, I give the stage to Shira. The title of her talk is Dynamics of Dry Intrusions and Their Relevance for Extreme Weather. Thank you, Shira.
Yeah, thank you so much, Daniel, for this for the kind invitation and also for this nice introduction. I'm very happy to see you all online. So thank you very much for logging in, and hopefully I can also meet you in person at some point in the future, near future. So yes, as Daniel said, I will talk about dynamics of dry intrusions and their relevance for extreme weather. This is a part of what we do in our group, which I thought would be good to talk about to you guys, since this is also how me and Daniel got together. But actually, I just want to say in a few words that in the group we are also interested in other topics. So this has a dynamical kind of focus, but we also focus regionally on the Mediterranean region, and there we study weather systems, interactions, and high impact weather. Specifically in this region. So this is another expertise. If you're interested, I'll be happy to discuss this later. But today I thought it's good to show a kind of an overview talk, summarizing some of our latest work at the Weizmann Institute. So naturally, this is work that is done by this long list of wonderful colleagues at the Weizmann Institute, also in collaboration with Jennifer Cato from Exeter and Virendra Gata from Argonne National Lab. And so I will talk about dynamics of dry intrusions and their relevance for extreme weather. And by extreme weather, I mean many types of extreme weather. So for example, strong surface winds, heavy precipitation, extreme temperatures, and also their unique combinations that drive events like wildfires, dust storms, or poor air quality events. And in the mid-latitudes, there's naturally fundamental understanding that extratropical cyclones, so low pressure systems, are key for many of these extremes. And so, as you all probably know, extratropical cyclones are not a symmetric feature. They're highly antisymmetric. So they have this hook-shaped cloud band and a rather drier side behind these frontal structures. And so many types of extremes like precipitation are kind of expected to occur in under this area, which is actually governed by moist ascending flow. And since this is a complex system, it is very useful and insightful to consider the actual motion of air around these systems, which is not just, cyclonically turning around the center like a tropical cyclone, but they have a complex structure, but a coherent one that recurs in many of these systems, despite a large case-to-case variability. So these typical airstreams around the cyclone give us a lot of insight. For precipitation, that's perhaps the most obvious thing to note. What I just said is that it is moist, slantwise ascending flow in the warm conveyor belt airstream forms this hook-shaped cloud structure with precipitation along the cold front and above the warm front, sometimes with embedded convection and high impact in this sense. But other types of extremes are less straightforward to associate with a cyclone, and this is where the other aspects come in. So obviously, cyclones are complex systems. As we all know, they involve not only typical airstreams around it, but when considering how these systems affect the near-surface weather and its extremes, we have to consider many things. For example, mesoscale frontal systems, of course, the upper-level dynamics and the meandering of the jet stream, the embedding of convection in microphysical processes, and also topography and other types of interactions on multiple scales. So the focus of my talk today will be on the dry intrusion aspect of these mid-latitude cyclones. And this is actually a slantwise descending flow behind the cold front of the cyclone. So let me introduce this now. And this is obviously a three-dimensional structure. So let's look at this schematic from the early work of Danielson, where you see the low pressure system right here with its fronts, the warm front and the cold front. And the dry intrusion airstream is a synoptic scale, slantwise descent of air towards the equator from the upper troposphere to the cyclone cold sector, where these airstreams that are here noted by these arrows, they fan out behind the cold front and fill up the cold sector of this cyclone, actually in this area of the dipole between this low pressure system and the high pressure that follows. And with regards to relevance for surface extremes, so there have been works, mainly of Browning in the North Atlantic, and also our work for the Mediterranean with Heini Burnley, noting that these types of airstreams are related to strong surface winds. You can imagine this high momentum air reaching the near surface. But I'd like to highlight that there are many other good reasons to care about these types of flows. So as you can imagine, these are dry areas this air that further descends, so it's very dry. It has a distinct albedo, and so it's important for its radiative transfer properties. These airstreams can also transport trace gases, especially when they originate in the stratosphere. They can transport it to lower latitudes, to lower altitudes. And as Daniel noted in the beginning, this long-range transport from the free troposphere into the boundary layer can affect local aerosol population, CCN properties, and many interesting phenomena regarding these fields. It was also noted that these types of flows can affect monsoon progression and precipitation variability. So I think that there are many different types of reasons for different kind of scientific atmospheric communities to be interested in these systems. But perhaps since there was no strict definition of this feature, I think there are many interesting and fundamental questions that remain unresolved, and this is what I want to focus on now. So from the dynamical perspective, I want to ask for this talk, well, if we look at the schematic, then what is this mysterious point? Where do they actually originate, these airstreams? Then we know that they descend quite substantially. So how do they influence the planetary boundary layer below? And in the horizontal direction, how do they influence the cold front? Here we see this very strong deformation structure. Well, do they actually reach the surface? If they do, it should matter a lot. You know, as I said before, for many different reasons, but also for extremes. If this air mass reaches the surface, it can affect surface extremes directly or indirectly, as I will show. And so this leads me to these more practical questions of the relevance of these features for extremes. And I'd like to ask, well, are they relevant to extremes? Which ones? And what are the underlying mechanisms? So according to these questions, this talk will have two parts to address these two aspects. And I thought I should, sorry, oh, I went backwards. I thought we should go actually backwards. So I will first refer to the relevance to extremes. I think this will also provide like more motivation to then understand these dynamical questions, and I will refine these questions later on. So let me start with a definition. As I said, there was no agreed definition for these airstreams, which mainly resulted in a collection of different ways to look at this feature, and more sporadic, let's say, studies. And I think we should have a definition that will allow some climatological understanding using, for example, reanalysis data. So this is what actually I did in my postdoc in part of my postdoc at ETH Zurich. I was very fortunate to learn the Lagrangian analysis tool, Laganto, developed at ETH. And we applied it to over 40 years of reanalysis data. So we take a Lagrangian perspective, because this is a Lagrangian feature, and we can identify these based on the wind field in reanalysis data, ERA interim or ERA 5 now, based on the descent property of these air masses. So what we do to diagnose them in reanalysis data is, well, we basically calculate forward trajectories using this tool kind of everywhere. And we only select the ones that descend at least 400 hectopascals within 48 hours. And these are dry intrusion trajectories. And so I will show you in a minute one example. But in the talk, I will also always try to generalize our findings to some climatological and general properties, since we do this for the whole of the ERA 5 data set from 1979 to almost today. Right, so let me now start with an example. Let me start with this water vapor channel image of one single event. I hope you can recognize the coastline here of the UK and the Western Mediterranean here on the bottom right corner. So obviously we're looking at this dry slot. And let's see how it evolves during 24 hours. This is from a day in October 2014. So you can see how it actually propagates over the UK, Western Europe, over the Alps here, and all over to all the way to the northwestern Mediterranean, where we have this very impressive front developing on its leading edge. And actually, I was there in Zurich at the time, and I remember experiencing very strong winds. So if you look at this upper left panel, you see wind gust measurements from the top of the building at ETH. And in that evening, wind gusts reached over 100 kilometers per hour. So almost jet stream wind speeds all the way at the surface. And well, if you look at these reports from the European Severe Weather Database, so all these yellow squares indicate strong wind, severe wind reports. And when we had this frontal structure, there were also reports of heavy rain, large hail, and even 2 tornadoes here in red. So it was a very interesting event that also brought the first snowstorm in the Alps for that season. There was a lot of damage all over this corridor where the dry intrusion actually passed. So how do we now go and study these systems? So we take the Lagrangian perspective, as I just explained. And when we do this at every single time step in the reanalysis period, this is what we get for this same day. So here you see a bunch of lines, colored lines. Each line represents an air mass and its trajectory, and it's colored with its pressure level. And these these set of dry intrusion trajectories, you can see that they descend from the upper troposphere near southern Greenland, and they descend towards Europe and the northwestern Mediterranean when they then fan out behind this low pressure system, this cyclone in the Mediterranean. So we know that it caused severe winds, and if you're familiar with this area, you know that actually this is a hotspot area for strong winds in southern France. It's called the Mistral wind. And so we wanted to generalize this case and ask, well, what happens to the Mistral wind when it's actually embedded in this large scale feature? So this is what PhD student Jonathan Givon did. And each circle here, each marker represents 1 day in the reanalysis period. And it shows the wind speed in the Gulf of Lyons in the northwestern Mediterranean in southern France, and the relative humidity in that same day. And you can see that when the Mistral is embedded in a large-scale dry intrusion, in which we have the data for, as I said, for 40 years, we know that we can see that statistically these are the strongest wind days, and they're also the driest compared to Mistral days that are not embedded in dry intrusions, and of course compared to all other days that have no Mistral detected. So we can see already here more evidence for the link between dry intrusion occurrence and strong surface winds. So now let's move on and ask, well, okay, what happens when these types of features reach over land and, for example, over the Sahara Desert? Does it affect, for example, dust concentrations? So in this study, let's look at another example. So again, in this plot here, you see these lines again. So these dry intrusion trajectories colored with pressure. In this example from March 2018, we see that they descend rather meridionally over Western Europe towards Northwest Africa. And they're actually steered by this upper level jet. So this green line shows the meandering of the jet, represented as the 2 PV unit contour on this isentropic surface in the upper troposphere. So you see how these airstreams are actually steered by this Rossby wave breaking event. And they descend southward in between this dipole structure of this Mediterranean cyclone and this anticyclone over the Azores. And I've marked this, the so-called dry intrusion outflow in this blue line. Basically, it represents the lower tropospheric portion of these trajectories because we think that maybe their shape can be connected to surface dust concentrations. So what happened on this date? Well, we can have a look at the dust optical depth data from the CAMS reanalysis. And look at this beautiful dust front. So very high dust concentrations or integrated dust loadings are observed on this date, and they are shaped along this leading edge of this dry intrusion outflow. So basically, if you now compare it to this conceptual diagram, it's very similar. So you have these dry intrusions descending between this dipole structure, fanning out behind this cold front, and in this case, it's actually a dust front. Now let's look at another actually quite famous case from March 2004 for this region. Look how similar it is. So again, a different case, dry intrusions with this rather massive outflow shape this this extreme dust front. And so it's very nice that we can also look at this animation from the satellite image where the dust is colored by this pink color. So airborne dust is colored in pink. And you can see how the dust kind of flows exactly like these dry intrusion outflow trajectories. So very independent data sets. So, sorry. It appears that these two cases are quite extreme. They're well known in the literature already. The dust concentrations were extremely high. In green, I enclosed these areas where the WHO thresholds were passed, and you can see that they actually covered the entire North African continent and also parts of the Middle East in these two cases. And this is how the island of Crete looked like in this March 2018 case. So we thought, well, we think dry intrusions can be important for these cases, and let's try to generalize these findings. So we have data of dry intrusions globally since 1979, and we have the canvas reanalysis available. It was then for 16 years. So what we try to do there is to automatically match these features and try to make generalizations or climatological understanding of such events. So we applied a matching algorithm between these dry intrusion outflows, so again, the lower tropospheric portions of these trajectories, and objects of high dust optical depth. And we kind of asked them to be together. So whenever they were close enough to each other, we kind of said, okay, this is an event of a matched dry intrusion and dust event. And by doing this is, by the way, the climatology of dust optical depth over these 16 years, from which we got these percentile thresholds. When we did this matching, we found 325 events during these 16 years. So quite many events. Actually, it's quite a loose criterion. Small objects are also considered. And we can now make generalizations, as I said. So maybe the first thing that we were interested in was to look at the seasonality of these events. And this is what you see here. So this is the occurrence frequency by month of these matched events in the yellow bars. And you can see how they actually peak in late winter and spring. It roughly follows the climatology of dry intrusions objects that peaks in winter. But it's also modified by the climatology of these dust optical depth, dust objects that actually peak in summer. But in summer, we hardly have any dry intrusions, so we have very few. So basically, this is 1 or 2 events in summer during these 16 years. Right, so what can we say about these events? Well, we further looked at the intensity of the dust objects, the maximum intensity, also the mean intensity is very similar. So I show here only the maximum. And now we take all of them together to try to generalize again. So we look at this intensity with dry intrusions here in red and without, compared to the climatology of all of these dust objects by month. So it varies a lot by month, but actually for each month, especially for the ones where we have more than just a few events, so maybe excluding July and October, the ones with dry intrusions are more intense in terms of dust optical depth. So in this paper, or these 2 papers, we also looked at the size of these events, the intensity of these events, and also at coherent precursors. We found out that during these matched events of dust with dry intrusions, we have quite coherent precursors over the North Atlantic concerning the jet stream, already 5 days before these events. So this suggests that these events that are actually kind of the more intense, the larger ones that peak in winter and spring are also more predictable, at least 5 days in advance. And so this was a regional study over the northwestern African region. But in our ongoing work, we also find indications that dry intrusions are important for the Arabian Peninsula and in East Asia as well. But this is still a regional study. But let's now go global. So we have data globally. And in this map, you see the winter climatology of dry intrusion outflows. Again, this lower tropospheric part of these trajectories. And I show it only for winter here of both hemispheres because they peak in winter. And you can see that, well, roughly that's kind of between 5 to 15% in the lower mid-latitudes. And since these outflows basically fill up this cold sector of the cyclones, now concerning extremes, one can ask, well, do they actually also correspond to the most extreme cold temperatures, not just cold temperatures anomalies? And this is exactly what we asked in this work. So in this master project, we asked, well, how many of the lower 5 percentile coldest local 2-meter temperature days occur during dry intrusions? And this is what you see in this map, in the green shading. This is the fraction of these days that have dry intrusions. And you can see that it's in some areas, it's very green. So like above 60 or 80% of the days of the extremes, we have dry intrusions. And here you see a zonal mean of this number. Actually, the more extreme one of the lowest percentile, so not 5%, but 1%, or even show higher values in the zonal mean. And if you compare it to the random or climatological dry intrusion frequency, which is roughly 5 to 10% here in the red, you see that they're actually more tightly connected. They are more probable if they are conditioned by the extremes. And this association can be sometimes 4 times the natural frequency. And another interesting finding here, I think, is that actually these high values of this association are not found where the dry intrusions are most common. Let's look at it here in the zonal mean, but actually more equatorward. So in areas where the dry intrusions are even more rare, in the subtropics, even tropics, then they completely govern these cold extremes. Right, so I can come back to this perhaps in the end, but we were kind of fascinated by this aspect that dry intrusions can even reach tropical latitudes, and we noticed that now, considering the southern winter, in one location globally, we have this even cross equatorial flow. So dry intrusions from the southern winter cross the equator to the northern hemisphere, and it happens only here in the Indian Ocean. And so here we thought, well, okay, interesting. It's interesting dynamically, but now I'm talking about weather extremes, and we wanted to ask, well, does it influence the Indian summer monsoon precipitation, because here it's summer? And so if we have this inflow of dry airstreams, perhaps it causes monsoon breaks, because there's a high variability of the day-to-day precipitation during the monsoon season. So here you see a seasonal mean of precipitation in this area. And now let's look at the anomaly. Let's look at the anomalies of precipitation following these intrusions that happen roughly 2 to 3 times per year. And this is what we find. So these are precipitation anomalies. And you can notice that they are definitely positive. So there's actually more precipitation during the days following dry intrusions. One of the famous cases here is the Kerala flood of August 2018. And when we looked at this further, and I encourage you to have a look at the paper, it's a fascinating story, we find that actually the enhancement of moisture transport towards the monsoon region and the Indian subcontinent is the triggering of very intense ocean evaporation hotspots. And I will come back to this in a minute. So this is now goes into the dynamical questions that I want to ask. So let me summarize this first part of the talk. We saw that dry intrusions are relevant for strong surface winds, for cold temperature extremes, for dust storms, and for precipitation extremes downstream. And so now I want to focus on the dynamical questions, and I want to focus on rather briefly on this question. So how are dry intrusions and the cold fronts related in the horizontal direction? And now going into the vertical direction, I think it's important to understand how dry intrusions interact with the boundary layer below it, because here the intuition kind of breaks, right? We have the descent of air. So this air kind of by definition warms up adiabatically a lot. And so what happens to the inversion layer? Does it get enhanced? If it does, then does this air actually penetrate the boundary layer? And how does it come together somehow with a cold anomaly that we observe, rather than a warm anomaly? Do they actually reach the surface? And if they do, then how do they influence air-sea interaction? So these are the questions that I will answer now in the second part of the talk. But first, the fronts. So quite briefly here, right. So here we identified both features, dry intrusion outflows, as I said before, based on the Lagrangian criterion, taking only the lower tropospheric portion of the trajectories, creating these 2-dimensional Eulerian objects of dry intrusion outflows here. Then we also identified objectively cyclones and fronts that trail from extratropical cyclones using a thermal front parameter that is based on gradients of wet bulb potential temperature. And we again applied the matching algorithm on reanalysis data for almost 4 decades, matching the 2 objects together. So basically requiring that they they touch one another when we expand the front line. It's just a technical thing to make them to match them. And when we do this, we get thousands and thousands of fronts that match with dry intrusions, and we can compare them to statistics or to characteristics of fronts that do not match with dry intrusions. So maybe the basic characteristic of a front is its intensity. Intensity in terms of wet bulb potential temperature gradients across the front. And this is what you see in this two-dimensional histogram, showing the maximum front strength in the x-axis and latitude in the y-axis, now looking at the northern hemisphere, but in the paper we also looked at the southern hemisphere. And now you see all kind of data of fronts with dry intrusions in red compared to fronts without dry intrusions in black. And what you can see that they have a different kind of distribution with latitude, fair enough. But you also see that there's a longer tail towards more intense fronts with dry intrusions. And when you do the global average for the northern hemisphere here, we find that actually they're more intense by 13% when they have this dry intrusion matching behind them. So another characteristic of the front here on the bottom left side is the front length, or in this case area, but I mean the width is constant kind of by construction, so it corresponds to the front length. Look at this. So here the front length is actually longer by more than 100%. When these fronts are matched with dry intrusion. So this matching kind of really gives the impressive fronts that are also more intense and longer. And so front intensity, we know that it's kind of generally speaking connected to precipitation. So in this here we also looked at precipitation within this front area. So average, not sum. So it doesn't take into account the different lengths. So just average in this area. And we found that precipitation is very much enhanced in the presence of dry intrusions behind it. Right, so that's it about this part. And now I want to talk about this vertical direction that I mentioned, the interaction with the boundary layer below it. So now let's look at the Lagrangian perspective and try to learn how this air mass of the dry intrusion evolves as it descends slantwise down in the troposphere, also equatorward. Notice that it's not a directly downward descent, it's slantwise. So in these box plots, what we see in all of them is the time evolution of several parameters along these dry intrusions. These are boxes because they include in them more than 28 million trajectories globally year-round. This was still era interim. And I put these vertical lines to mark the time window of the 48 hours where the descent is actually defined. Remember, the criterion for all of them is a descent or basically an increase of pressure that you see here in the upper panel from an increase of at least 400 hectopascals in these 48 hours, which they all have to fulfill. So this is what we see here. But actually in the calculation, we also kind of extended these trajectories backward and forward in time. But let's now concentrate on this 48-hour window. So we see this increase in pressure, which, as I said before, corresponds to adiabatic warming. What else can we learn from this? Let's look at the specific humidity content of these air masses. We have these values from era interim. When we have these trajectories, we can also trace other variables from era interim, given the location and timing of these air masses. So in 4 dimensions. Basically what we see here is that these air masses are moistened as they descend down into the boundary layer. So this is maybe a first indication that there is some kind of mixing going on with the lower, more moist boundary layers. And so then I asked, well, okay, so what happens below these descending airstreams? And I wanted to look at the stability right below it to see if there is some possible mixing into the boundary layer. So as a proxy for this, I looked at the difference in equivalent potential temperature between 800 hectopascals and 950 hectopascals. So whenever we have a negative value, it means that it's potentially unstable. And if you look actually here, this is the 0 line. The 0 line is roughly here. And by by the time of 24 hours, so midway through the descent, we see that actually more than 75% of dry intrusion trajectories have potential instability right below them, at least considering these two layers. Now, another way to look at this is to look at the boundary layer height anomaly. So the boundary layer height is parameterized in error interim. It has its limitations, of course, but let's still use what they have. And we can look at the anomaly of this boundary layer height wherever the dry intrusions are. Let's look at the boundary layer just below it in the same kind of horizontal location. And let's look at the anomaly of this height compared to the same month and the same time of the day. And this is what I show here, but in terms of pressure. So basically negative values would mean higher, so thicker, or let's say, yeah, thicker boundary layer. So again, roughly more than 75% of dry intrusions have anomalously deep boundary layer below. And this suggests that there is something happening there. So maybe the dry intrusions are mixed into the boundary layer by potential instability, and the boundary layer deepens. And I think here at this point, there's kind of a limit to what you can do with reanalysis data. And here I was very happy to learn about the DOE campaign in the Azores Island that Daniel mentioned. And so in this collaboration, we used these data of the ARM site in the Graciosa Island, which is found in the Azores Island in the eastern North Atlantic. So if you look at this kind of zoomed in map that I showed before, this is the location, and dry intrusions occur here about 6% of the time in winter. So we can kind of identify these events and see how different boundary layer parameters are kind of changing with the arrival of these air masses, and we have enough statistics. So here we have data from 3 years. We only looked at the winter month DJF using radiosonde data and a laser ceilometer that allowed more detailed information of the boundary layer structure and height and so on. Right, so let me start with an example. Here is again dry intrusion trajectories colored with pressure. You see how they descend, I mean, in this case, rather zonally, and they arrive into the area of the Graciosa Island. And so now let's look at this panel on the right. It's a bit complicated, but I will walk you through it. This is now a vertical cross-section at the island with time. So we look at the evolution of this vertical cross-section. The shading is specific humidity. And the lines are potential temperature. So the red is potential temperature and the black is equivalent potential temperature. And these dots are the dry intrusion trajectory intersections with this column of air with time. And you see how they actually arrive around the 30th of December 2017. And they kind of, you have more and more air masses that arrive. This is just an example of a single starting time. And let's now look at how this middle and lower tropospheric profile responds. So you see straight away how the specific humidity decreases, and it happens not only in the middle troposphere, but also all the way down to the surface. Also near the surface, you have this very strong drying. And also cooling. So if you look at the potential or equivalent potential temperature contours here in red, you see this very strong cooling. So what we did again, using these objectively identified dry intrusions and cold trailing fronts, we identified every time step with a dynamical regime. So we can identify, of course, all time steps with dry intrusions around the island with some threshold of 1 degree around it. And we identified all front passages. So before the dry intrusions, there's a cold front passage. We also have cold fronts, as we saw before, that are not followed by dry intrusions. So these are marked here in this non-dry intrusions fronts. And we also have a 24 hours that we call this the post-dry intrusion stage or the recovery stage, right after the occurrence of dry intrusions, to kind of make this distinct from any other reference period where we have either just a front or nothing, no dry intrusions and no fronts. And so let's now, again, generalize this case. We have data for the winter months of 3 years. So we actually identified 31 events similar to this. And we labeled all the time steps now using these definitions. Again, these dry intrusions are 6% of the time. And we can look at actual radius-on data now averaged for these different regimes. Let's first look at specific humidity here in this corner here. So specific humidity is the driest during dry intrusions. So this is confirmed. It's still rather dry during the 24 hours after. You see it in this cyan color of the post-dry intrusion stage. Of course, very much drier in relation to all other reference periods where we have the frontal passage and the more moist conditions naturally. But maybe interestingly, if you look at the relative humidity, you can notice here that actually just below the boundary layer top, the dry intrusion regime is actually the most moist. Right? So this, of course, happens because it's also the coldest. So if we now look at temperature here, you see that the dry intrusion regime has the coldest profiles all along the lower troposphere. You can also see it in the potential temperature. Equivalent potential temperature also shows the strongest potential instability. And if you now go back to the temperature profile, it also indicates that there might be a stronger inversion during dry intrusion, during the dry intrusion regime. But we have to be careful because these are, of course, mean profiles and it's very noisy. So I don't have time to show it, but actually we looked at the individual profiles and we found out that yes, indeed, during dry intrusions, the inversion layer is not only strongest, but it's also thicker and also higher, as you see actually here in this mean profile. So we do have a stronger inversion during these periods. So how does it come together? Well, let's also look at the boundary layer top height. According to these radius-on profiles, there are many ways to diagnose the boundary layer top height, as we all know. So we looked at it, and we looked at gradients of temperature and humidity using these different methods that are detailed here. Also using the bulk Richardson number based on these radius-on profiles, and as measured kind of independently from the ceilometer data here on the right. And they're colored by these different regimes. And first of all, as you can see, there's a lot of variability. And this is kind of well known also in this paper. They indicated the huge variability depending on the method that you choose. But still, whatever method you choose, you see that it's the highest during dry intrusions. So you see this red box kind of being the highest, whatever method you choose. And let's take this now maybe more qualitatively. So we now see that using these measurements, yes, indeed, the boundary layer top height is the highest during dry intrusions. And again, it remains rather high for 24 hours later also. So in summary, until now, we have the cold and dry intrusion air that enters the boundary layer. Sorry, I forgot to say it before, but it's important, so I go back right just a bit. You can see that these actually enter the boundary layer, and the boundary layer height here in reanalysis still is shown by this blue color, and you can see how the dry intrusions basically fill up the boundary layer. So this is indicated by the reanalysis data. So we have the dry anomaly, the cold anomaly. It enters the boundary layer deepens, and we have a stronger inversion. So if we have this now relatively dry and cold air mass that reaches the ocean surface, I think it's also important to consider surface fluxes, surface turbulent heat fluxes. So we can expect them to kind of peak here when we have this dry air mass and cold air mass reaching the surface. And so here I show briefly a map during this time step that shows the dry intrusion outflow covering this area. It's the driest. Here you see it with a specific humidity at 850. And here I show the latent heat flux, the surface latent heat flux, so ocean evaporation. And we also see this hotspot of ocean evaporation in this area. And it's not surprising because it's parameterized according to this bulk formula where we have a larger moisture deficit in dry intrusions. We have more enhanced wind speeds. This is for latent heat flux, but also for sensible heat flux, we have a similar triggering of heat fluxes by the cold, by the temperature difference compared to the SST. So we try to, again, to generalize this. And here we look at the frequency distribution of latent heat flux on the left and sensible heat flux for the different dynamical regimes. And basically what you see here, just to be brief, is that we have this longer tail towards the highest values during dry intrusions, and some recovery during the post-dry intrusion stage. So we also have this now enhanced surface fluxes. So under dry intrusions, we have the strongest contrast with the ocean surface, both in terms of temperature and specific humidity. And we also have the potential role of wind speeds and instability to trigger these surface fluxes. We also saw this in other regions, such as the Mediterranean, where it really creates a hotspot for deep water formation. So it's not just in the Azores. So now I showed different regimes, but let's put it now in the time kind of time evolution. So here I show the same cross section as before, but now it's a composite for all 31 events. And it's centered around the first arrival of the dry intrusions here at time 0. And you see this very strong drying throughout the troposphere all the way to the surface, and the cooling that is imposed by these dry intrusion events. So let me summarize what we understand from here. We saw that dry intrusion events lead to deepening of the boundary layer, but how does this actually happen? So first, we saw the deepening process that starts top down. We have an induced low theta E air on top of the boundary layer that creates a negative potential temperature, equivalent potential temperature gradient with height and potential instability that then presumably allows the mixing of this air into the boundary layer itself and causes its deepening. At the same time, we have a stronger inversion. So how does it come together? So here I think we should adopt a three-dimensional view and not a single column view, because there's very strong advection in these cases. It's not just a vertically downward descent, it's coming with a strong advection. So basically, when you think about it, this relatively cold and dry air enters the boundary layer from the sides and creates a cold anomaly from below. So the strong inversion is created not by warming from the top, but rather by a cold anomaly from below, from the boundary layer itself. And this cold and dry air, together with a strong wind gust and unstable conditions, triggers very strong surface fluxes. And I think this now kind of enhances this deepening of the boundary layer by this time bottom up. So both enhancement of this deepening of the boundary layer, but at the same time, it also then kind of causes the recovery from these conditions, because the new surface fluxes kind of replenish the moisture deficit or the cold conditions, right? It heats up the air and it moistens the boundary layer. Right. So in this paper, actually, we also looked at clouds in these different regimes, and I encourage you to have a look. But I think since I'm running out of time, I moved to my last result slide, which I didn't forget, because I also asked, well, where do they actually originate? Where do these airstreams originate? So here we looked at this actually regionally, but it doesn't matter. It applies to many other regions. We looked at the North Atlantic European region, where we could identify over 800 initiation events. So not single trajectories, but events of sets of trajectories in reanalysis. And here I show composite plots around these clouds of initiation events. So these initiation events, or the location of the trajectories during these initiation events, are shown in this cloud here. So all these composites are centered around these initiation events. And here I show a zonal vertical cross-section of PV and potential temperature. And on the right-hand side, I show the anomalies of these two fields. Basically, if we look at PV here on the upper left, you see that they preferentially occur below dips in the tropopause, basically a trough here behind the trough. So basically where we have large-scale forcing for descent. And when you look at the anomaly, right, it occurs first of all, it occurs in the upper troposphere, mostly. So hardly ever does it occur in the stratosphere. That's That's an important point. It has some implications. But in the upper troposphere, it occurs just below and to the west of these positive PV anomalies. And this is important because in terms of potential temperature, it occurs in areas of negative potential temperature anomalies below these PV anomalies. And this is important because these initial anomalies are then advected along these descending isotropes all the way to the surface, and this actually affects the eventual cold anomalies that we observe very often. And I didn't have time to talk about it, but we looked at this further in the context of cold fronts and wildfires. But I think I'll stop here and summarize the two parts of the talk. So the dynamical interactions part, let me just say again briefly, the origin is behind and below positive PV anomalies in the upper troposphere with cold temperature anomalies already at the initiation point in the upper troposphere. When they descend down, they penetrate the boundary layer and they often reach the surface. They advect dry and cold air into the boundary layer. They fan out in the cyclone cold sector behind the cold front. They destabilize the lower troposphere and enhance winds. The boundary layer deepens. We do find stronger inversion still, but for another reason, because of the cold anomalies. And this also enhances surface fluxes. And then it enhances the fronts just ahead. And so I think that now when we understand these processes, we can also further understand why are these dry intrusions related so tightly to many types of extremes. So strong surface winds is one aspect, but also intense frontal precipitation can be at least partly attributed to dry intrusions. Also cold temperature extremes and dust that is very much enhanced under these strong wind and unstable conditions. Downstream precipitation can be attributed to these intense ocean evaporation hotspots. And again, unfortunately, I didn't have time to speak about it, but they also correspond to to many of the largest wildfires observed. And in this study, we focused on Southeast Australian historical fires, and this is just accepted. So in terms of outlook, I think what I showed kind of prompts us to ask, well, how do models represent these processes? If we know that these processes, for example, the interaction with the boundary layer is important for extremes and for getting the surface conditions right, we should hope that the models can get this information, this process represented well, both numerical weather prediction and global climate models. And this is something that I think we should clarify. Then I mentioned predictability quite briefly in the context of dust storms, but actually, well, do extremes that are connected to dry intrusions on this large scale are more predictable than other extremes that are more local in nature? Perhaps yes, because there's some degree of predictability to this large scale flow. But this is given that the models get it right, get this more subtle interaction right. And I think the results also have consequences on our understanding of the future occurrence of extremes, because the future of cyclone occurrence should relate to the future of also cyclone impacts. But the cyclone impacts are another layer of complexity. There's a lot of case-to-case variability in cyclones, and different cyclones have a kind of a different surface impact. I think it's also important to remember that cyclones can project extremes also non-locally, so not just at the cyclone center. As we showed for the cold extremes, the cyclone can occur in the Mediterranean, and the actual cold extreme can even reach the tropics, or the subtropics for sure. So quite far from the cyclone, and this is because of the dry intrusion flow that extends sometimes a few thousand kilometers equatorward. And this is true also for air-sea interaction in the tropical latitudes. And this is something that we are very excited about. And we also see that there's an important contribution there to tropical ocean evaporation by these flows from the mid-latitudes. Right, so with this, I'd like to end, and I'll accept any kind of question, and thank you very much for your attention.
Thank you, Shira. This was a really nice and very clear talk about dry intrusions. I'm sure their question. Wonderful. So I open the floor first. And before I take the first question, I just want to remind the graduate students, I forgot to mention that Shira has time afterwards. She will stay on this call in the Zoom and has time to meet with you. So please, graduate students, hang on and meet with Shira. Okay, so first question. So please, Edmund, go ahead.
Hi, Edmund.
Hi, Shira. Yeah, it was. Do you hear me?
Yeah.
Yeah. Okay. Great. So, yeah, it was great. It's a great talk, and actually, I have many questions, but in the interest of time, I probably will just ask you a couple of questions. The first question relates to what you sort of the last result that you showed is that the dry intrusion mostly come from the upper troposphere. Now we have this kind of schematic that there is a stratospheric air coming in, high PV, low humidity, and high ozone and chemical with the chemistry that actually seems like the stratospheric air. So how does that fit in? Because you're saying that only 1.2% of the dry intrusion from the stratosphere mostly comes from
true.
the troposphere.
So I'm sorry I don't have this as an extra slide. But apparently, of course, there are also stratospheric intrusions, but I think this is a different kind of feature in the sense that stratospheric intrusions do not descend very deeply. So of course, there are also many other studies on stratospheric intrusions, and they're important for these reasons because they can advect high PV and intensify surface cyclonic circulation and many other important things. This is why we also looked at this origin. But so I don't have this extra slide, but in my paper from 2017, I show a cross section along the descending dry intrusions together with the isotropes. And when you consider the meridional sloping of the isotropes closer to the tropopause, you realize that if you follow isotropes there from the stratosphere, they cannot descend very deeply to be identified by our criterion. So the isotropes that cross the tropopause only descend in the meridional direction, maybe 200 or 300 hectopascals, and not 400 that we detect. And the ones that do have this sloping have to start mostly in the upper troposphere. Perhaps I can send it to you later, but I think this is kind of my intuition to it. Yeah.
Yeah. Okay. Can I ask another question?
Yes, go ahead. Go ahead. I don't see a raise.
Yeah. And another question is that you related the dry intrusion with the fronts. So have you tried sort of relating the dry intrusion with the cyclone? It's kind of a, I guess it's the whole process, the cyclone.
Yes, exactly. So
yeah.
Exactly. Actually, it was our first motivation was to relate it to the cyclones and relate it to like cyclone properties. Technically speaking, we have to make decisions on how we relate them together. Basically, I think dry intrusions are more related to the upper tropospheric waviness that kind of steers it in the meridional direction, and so it has to descend along these sloping isotropes in the baroclinic zone. But yeah, you wanted to connect it to the cyclones, but how do you make this connection, technically? Because they are not in the same place. And this is when we actually came to think about the fronts. And these cyclones are actually connected. So these dry intrusion outflows are connected to cyclones because we only looked at fronts that trail from cyclones, and we separated it from fronts that are isolated. So in the paper, we also handle isolated fronts kind of separately, and cold trailing fronts from cyclones that we also identified based on the sea level pressure minima. And so actually the second paper here shows a front-centered perspective. So in the second paper, we show composites that are centered around the front, and then we also talk about the cyclones themselves. And or maybe as you can expect, dry intrusions preferentially occur near deeper cyclones Probably this is where we see the deeper slopes of the isentropes and more dry intrusions identified. So kind of everything is stronger, which is a caveat because we don't apply causation yet, or it's an association. Yeah.
Yeah, great. So yeah, I was wondering because that's something that I kind of expect, that you're more associated with stronger cyclones.
Yes. Yes.
Yeah. Well, I think I'll let somebody else ask.
All right. Yeah. Levi Silvers, please.
Hi, Shira. Thank you for your
Hi.
talk.
Thank you.
Yeah. I have perhaps a very simple question that I should probably be able to figure out from graduate studies years ago. I don't know. But if we look at the most basic schematic that you showed many times of the dry intrusion, starting at a point kind of in the upper troposphere and then coming down and spreading out, why does it spread out? I'm used to thinking of parcels as they move downward, kind of compressing and as they move upward, spreading out as the, in the lower density regions. And so I don't understand kind of dynamically or thermodynamically why it would spread out as it descends.
So I think the spreading out is not in the molecular sense, but if you consider many air parcels, and let's say a trajectory of each air parcel is an arrow, then they basically fan out because you have a deformation zone in between this dipole structure.
So is it more?
It's just a flow. It's just the kind of the ambient pressure distribution that dictates the flow. And in this area, it's quite coherent in this direction. And then later on, you have this deformation behind the cold front deformation zone.
Okay, so then is it kind of like if you drop a drop of ink into a flowing liquid, it's going to spread out and disperse very quickly, or we have the sensitive dependence on the initial part where the trajectory started.
So it's on
go to different spots.
It's of course on a larger scale. So each of these arrows is typically something like 80 or 100 kilometer in size in the horizontal direction, and let's say 20 hectopascals in the vertical direction. So it's quite it's an optic scale air mass. And it's not very quickly. It takes 2 days. So I don't know.
That helps. That helps kind of reformulate my thinking to where each, we're seeing a lot of different parcels here, and
but it's also part of
I guess.
Yeah, but it's also kind of how we do this trajectory calculation. Obviously, when you start in a single location, it's not in a single location. It's because if you start, in the trajectory calculation, we start in many locations on a regular grid in the upper troposphere, and we look for descending flows. And so maybe a better representation would be any of these examples where we have like a few starting points near each other. It's not a single point that diverges. Yeah.
But I guess the point is that the initial descent starts in a smaller region than where they end up near the surface.
Yes, this is true. This is true, and this is also true actually for things like warm conveyor belts that start in a well-defined region in the lower troposphere, and they usually fan out near the tropopause. So it doesn't matter the height doesn't matter. It's basically the kind of the chaotic nature. First we have coherent flows near the cyclone, but then after a few days, then typically we have the dispersion. Yeah.
Good. Thank you.
Minghua San, please.
Yes, very nice talk. I enjoyed.
Thank you.
Regarding the deepening of the boundary layer, you mentioned it's because of the advection of dry air into the boundary layer, making it deep. That means that air has to be in the boundary layer already. So when it advecs, it raises it. Another scenario I would think is you have cold air, dry air entrained into the boundary layer that promoted larger buoyancy and also wind shear. Therefore, the entrainment becomes stronger and the boundary layer becomes deeper. I thought this is actually an interesting modeling study for people to understand, say, why the boundary layer is deepened. I wonder whether you have any comments regarding this possible scenario.
I totally agree with this suggestion. I think it's probably a combination of all of these things, because this descent is slantwise. Basically, it's both advection and some kind of vertical entrainment that is caused by wind shear, and this destabilization that you also mentioned. So maybe the partition between the three is I think we haven't looked at that, but I think it must be a combination of all of these aspects.
Thank you.
I basically agree, but yeah.
All right, maybe let me ask the last, maybe the simplest question. You showed somehow a seasonal dependence and a southern hemispheric dependence. It looked like in the southern hemisphere there were less in wintertime dry intrusion events compared to the northern. I wanted to ask if that is right. I don't know if that is why that is, naively speaking, and why dominantly in winter. That is just in the northern hemisphere. It's just due to the jet stream or our winter mesoscale meteorology with the storms, low pressure systems, or why do we? Is there something else in terms of seasonal and
Thanks.
hemispheric difference?
It's a very good questions. The basic ones are, I think, the most important. I mean, so in terms of numbers, first, actually, when I looked at the numbers, it's quite similar in the two hemispheres, but the zonal distribution is very different. And you see it's more concentrated in the northern hemisphere. It's also true for the storm tracks in general. And we know that the two are kind of coupled. And what determines both this and the seasonality is I think the intensity of the baroclinicity. So the more meridional, the more intense meridional temperature gradients would kind of dictate everything. So the development of cyclones, and also the sloping of the isotropes, which then kind of lay out the landscape for the descent of this flow, which is quasi-isentropic. I mean, there is some radiative cooling, so there is some cross-isentropic flow, but it's basically very close to isentropic flow. So these isentropes, of course, slant downwards towards the equator. So whenever we have a meandering jet, Rossby wave breaking even, then these air masses are kind of forced to go into the equator, and then they have to descend to maintain their potential temperature. And this happens preferentially in winter because of the baroclinicity. And also with this partition into the ocean basins in the northern hemisphere, and less so in the southern hemisphere. I think this is kind of
great. No, thank you. Thank you. All right. If there are no further questions, then let us thank Shira again to make time this evening to give this wonderful seminar. So thank you.
Thank you. It was a pleasure.